Hello, welcome to Math 251, Calculus 1 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we will take a look at section 3.2. We will be looking at the derivative as a function. And so we've seen derivatives and we found derivatives at specific points, but those are just going to be numbers that gives us a slope of the tangent line at that point. But now we want to look at the derivative as an entire function. And so we're gonna see how to approach this symbolically and then look at the graph and then make the relationship between derivatives and continuity. And so this is our second difference quotient that we had and we used to define our derivative at a particular point. And we had f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. So that is at a particular point. But now, if we want this generically at any point, instead of putting a in, we can just leave it as x, and now we have a function. And so this is how a lot of our derivative shortcut formulas are going to be defined. We're going to use this to define it, to find a shortcut, and then after that, we'll kind of pack this formula away until we really need it again, because of course, it'll be easier to do things in a shortcut kind of method way. So symbolically, this is going to be our really super important formula for finding derivatives of functions and finding the derivative function of a function. Now let's take a look at some graphs of derivatives. So the graphs of derivatives, the idea behind this is to take a look at a graph of a function and try to see what the derivative is going to look like. So if we focus in on this particular graph over here, the original function is the square root of x. Now if we look at the values that are really close to 0, we can see that our slope is really steep, and a super steep slope that's going upward like this will tell us that the value of the slope is really high in the positive direction. And so if we get closer and closer to 0, it actually goes vertical. That's why we have an asymptote. On our derivative, for our derivative function, we have an asymptote as we get closer and closer to 0. Now if we go farther out, like 3, 4, 3.5 or 4, or whatever those values might be, then we see that our slope is getting less and less. And so this function will never have a vertical derivative, and so it'll never approach 0, but it's getting less and less steep, and so that means its slope is getting closer and closer to 0. And so those are some of the things that we're going to watch out for. But really the key to do this is you can't really apply it to this function, but in most functions that you're going to be dealing with, the key is to look for those horizontal slopes. And so as in this example, we have a couple of places where we look like we have horizontal slopes. Say at 3 and probably somewhere around -2, when those x values are -2 and +3, it looks like we have a horizontal slope. And so now we know that the derivative will be 0 at those points because the slope is 0 at those points, the slope of the tangent line. And then in between -2 and 3, we see that the graph is increasing. So this graph, if you were to graph your derivative, and those are the slopes of the tangent line, they would be positive above the x-axis. Whereas if we take a look at to the left of -2 and to the right of +3, we see that the graph from left to right, the graph will be going downward, and the downward slope will give us a negative value for our derivative. And so if you were to graph its derivative, it'll look something like this, where around -2 you hit your derivative hits the axis, and at +3 your derivative hits the x-axis. Between -2 and 3 your graph is increasing, and therefore your derivative will be above the x-axis because increasing is positive. And then from left to right, if you go to the left of -2, your graph is decreasing, so your graph will be below, your graph of the derivative will be below the x-axis. And likewise for anything that's past 3, your function will be decreasing, and so your derivative will be negative. Okay, so that's a quick rundown on finding the graphs of the derivatives with other graphs. So derivatives and continuity have a special relationship. If your function is differentiable, then it necessarily has to be continuous. So there's a theorem and a proof for that, and we'll take that, take the theorem and take that that proof as something that's going to be true for us. Now, it is important to say that if your function is differentiable, then it's continuous. But if your function is continuous, it doesn't necessarily mean it's differentiable. So there's an important distinction between those two phrases. One of them is true, the other one is not. If you have a continuous function, it doesn't necessarily mean it's differentiable, and the perfect example of that would be like the absolute value function, where you have a sharp corner and the function is not differentiable at that corner. And so that is a continuous function, but it's not necessarily differentiable. And then finally, we're going to, in this particular section, we'll be taking a look at higher order derivatives. And the higher order derivatives just means you take derivative after derivative after derivative. Now, the first derivative, we saw an application for that as the velocity, and then the second derivative is an acceleration. So any derivatives beyond that would just be described as the rate of change of that previous derivative that you had. So, for example, a third derivative could be seen as the rate of change of acceleration over time. And so the notation for this, we can use primes, but when we get past 3, the 3 primes, it's probably, the 3 apostrophes are probably the farthest you can go. So anything beyond that, we just put 4, 5, 6, but we put it in parentheses so that we're clear that this is a derivative and not being raised to a particular power. All right, that is our rundown for this section 3.2. And I hope this gives you a good head start with tackling the material. Okay, good luck.